Right now, you are sitting on a rock that's hurtling through space at a speed of 670,000 miles per hour. This rock is orbiting a nuclear furnace that is 1,000,000 times larger than itself. And this furnace is just one of 400 billion stars swirling in a galaxy so vast that it takes even light 100,000 years to cross it. But here's what will truly blow your mind. Our entire galaxy, with all its billions of worlds and countless civilizations that might exist, is nothing more than a single grain of sand in an ocean containing 2 trillion other grains of sand. If you enjoy journeys that change your perspective on reality, hit like and subscribe. Get ready. Here we go. Imagine you're standing in the middle of nighttime New York City. Lights stretch out into infinity in every direction. Buildings fade into the darkness on the horizon. Now imagine that this cityscape extends not just to the next state, but across the entire United States. Then stretch it across the Pacific Ocean all the way to Asia. Keep pulling it all the way around the entire Earth. And now, multiply that distance by 6 billion. You've just imagined the width of our galaxy. Scientists, using precise measurements, have confirmed that the Milky Way stretches 100,000 light-years from edge to edge. 1 light-year equals 6 trillion miles. This means our galactic home is 600,000 trillion miles across. To write out that number, you'd need a line of zeros that would stretch from your home to the nearest convenience store. But this is precisely where human intuition faces its first shock. Despite this overwhelming scale, our galaxy is just the first step on a cosmic staircase leading to an infinity our brains can't process. Every single point of light twinkling in the night sky belongs to our galactic neighborhood. The hazy band of stars stretching across the dark sky is what our spiral arms look like edge on. We live inside this cosmic city, embedded within its structure, like a single cell in a giant organism. From our vantage point, approximately 26,000 light-years from the galactic center, we can observe star-forming regions where new suns ignite. Each year, we witness stellar nurseries where gravity sculpts blazing spheres from gas clouds. Ancient red giants die in spectacular explosions, seeding the cosmos with heavy elements. All this cosmic drama unfolds on the stage of our local galactic theater. And yet, what truly makes this scale unsettling is not its size, but what it represents. Our galaxy is merely one unit in a hierarchy of structures that becomes increasingly immense and incomprehensible. Each new level of cosmic organization eclipses the one before it to such an extent that human experience becomes utterly meaningless. Standing here on Earth, contemplating galactic distances, we're akin to an ant attempting to grasp the sheer scale of North America. An ant might sense that something immense exists beyond its immediate surroundings, but it simply lacks the cognitive framework to truly comprehend continental scales. Humans encounter this very same limitation when confronted with the vastness of space. Our brains, having evolved for hunting on the African savannas, struggle to process scales that extend far beyond the confines of our world. This cognitive barrier serves as our first inkling that the universe operates on levels far removed from human intuition. Every cosmic structure we uncover forces us to abandon our terrestrial preconceptions and embrace scales that feel more like mathematical abstractions than tangible physical reality. The ancient Greeks believed that stars were holes in the celestial sphere surrounding Earth. Modern astronomy reveals that our galactic home alone holds mysteries that would far exceed their wildest imagination. Every telescope that gazes deeper into space uncovers new layers of cosmic organization, stretching towards horizons we can barely discern. Yet, compared to what lies ahead, our galaxy is merely one room in a cosmic mansion with countless floors spiraling into infinity. Light travels faster than anything else in the universe. Nothing can outpace a photon racing through the vacuum of space. Moving at a breathtaking 670 million miles per hour, light circles Earth 7 times in a single second. This cosmic speed limit represents the swiftest means of traversing distances within our reality. And yet, even light, physics' undisputed speed champion, takes 100,000 years to travel from one edge of our galaxy to the other. Consider what that means for our perception. The light that left distant stars in our galaxy this evening began its journey when the first humans were just learning to harness fire. Photons reaching Earth from the opposite side of the Milky Way embarked on their journey even before the advent of writing. These ancient particles of light carry information about stellar events that occurred when our ancestors were just discovering agriculture. Scientists use this light travel time as a cosmic measuring stick. When astronomers observe distant galactic regions, they see them as they were thousands of years ago. The galaxy we observe today is, in essence, a patchwork quilt of different temporal eras. Nearby stars show us recent events. Distant star clusters reveal ancient history. We never see our galaxy as it is right now, but rather as a time-averaged picture spanning millennia. This temporal displacement creates one of the strangest confirmed facts of astronomy. Every photograph of our galaxy shows several temporal periods simultaneously. Light from different regions left its sources at different historical moments. To look at the Milky Way is to look into the past over a span of time that is longer than all of human civilization. But this journey through time becomes even more dizzying when considering the galaxy's rotation. Our entire galaxy rotates like a cosmic pinwheel. The solar system completes one orbit around the galactic center every 200 million years. In the time light travels across our galaxy, the entire structure manages to complete almost half a rotation. The galaxy literally changes shape while light travels between its regions. Even more concerning is what this implies for interstellar communication. Any attempt to send a signal across our galaxy confronts this fundamental barrier. Radio waves and laser beams travel at the speed of light. This means that galactic communication demands patience on a geological timescale. If an alien civilization on the other side of our galaxy sent us a message today, it would be received by the great-great-great-grandchildren of our great-great-great-grandchildren. This communication barrier means that our galaxy can never function as a single system. Different regions operate independently, isolated by the fundamental limit on the speed of information transfer. What seems like a unified cosmic structure is, in reality, made up of countless independent zones, each evolving unaware of its distant galactic neighbors. Ancient photons reaching us today carry messages from a galactic past, a past we can observe, but will never be able to visit. Every star that we see tells us about the conditions that existed before our species learned to gaze upon the night sky. And yet, this problem of galactic communication is merely the smallest of the challenges that we face as we try to comprehend cosmic distances. Step outside on a clear night and find the brightest star in the sky. That luminous point of light is Sirius, which burns 25 times brighter than our sun. It appears so bright that ancient civilizations built their calendars based on its movement. To your eyes, Sirius seems close enough to be within reach of a very tall ladder. The established reality completely shatters this illusion. Sirius is 8.6 light-years from Earth. That's a distance of 51 trillion miles. If you could travel by car at an ordinary speed to this nearest bright star, the journey would take 300 million years. You would have to drive non-stop at a speed of 100 kilometers per hour since before complex life even emerged on Earth. But Sirius is practically our neighbor compared to typical galactic distances. Most stars in our galaxy are separated by gaps so vast that they defy human comprehension. The average distance between neighboring stars is 4 light-years. In cosmic terms, this is an almost perfect vacuum, occasionally interrupted by tiny islands of matter. To visualize this emptiness, imagine our solar system shrunk to such an extent that the sun became the size of a basketball. At this scale, Earth would be a grain of sand orbiting at a distance of 8 meters, and the nearest star would be another basketball, located in another city, say, in Denver, if you started your journey from New York. All the space between these balls is, essentially, emptiness. This void has profound implications for interstellar travel. Even when traveling at the speed of light, journeys to the nearest stars take years. Conventional spacecraft, traveling at achievable speeds, would require tens of thousands of years to reach our closest stellar neighbors. The vast majority of our galaxy will forever remain inaccessible for human exploration. The void between stars also explains why contact with extraterrestrials seems so unlikely, despite the enormous number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they face the same fundamental barriers of space and time that isolate us. The universe seems to have conspired to separate intelligent species with chasms too vast for meaningful interaction. Scientists have estimated that our galaxy contains approximately 400 billion stars. And yet, these countless suns are scattered so sparsely across galactic space that each one exists in magnificent isolation. The night sky creates an optical illusion, making the stars appear huddled together, while in reality they dwell in a realm of cosmic solitude. This stellar isolation extends throughout our galactic neighborhood. Even in the dense central regions of the Milky Way, where stars are packed more tightly than in our outer spiral arm, vast empty spaces persist between individual suns. The galaxy, which appears so rich and populated in telescope images, is in reality composed mostly of vacuum. Reflecting on these empty spaces between stars gives us the first glimpse into the true nature of cosmic architecture. Matter is a rare exception, scattered across an all-consuming empty universe. We reside on tiny oases of substance, floating in an ocean of nothingness. But this galactic void looks positively crowded compared to the spaces separating entire galaxies. Imagine counting every single star in our galaxy. Start with our sun and move outward through the spiral arms. Count every red dwarf, every blue giant, every binary system spinning through space. Maintain a steady pace, 1 star per second, without stopping for sleep or food. You'd finish counting in 12,600 years. Confirmed observations from space telescopes show that our galaxy contains anywhere from 100 to 400 billion stars. The exact number remains unknown, because dust clouds obscure our view of distant galactic regions. Dark nebulae conceal star populations that we can only detect using infrared radiation. But even a conservative estimate of 100 billion stars surpasses human comprehension. Each of these stellar furnaces burns with the power of nuclear fusion. Every second, our sun transforms 4 million tons of matter into pure energy. Multiply that power by hundreds of billions of similar reactions occurring simultaneously across our entire galaxy. The total energy output of the Milky Way exceeds the energy consumption of human civilization by an amount that requires scientific notation to even write. And yet, this astonishing stellar population leads to a disquieting realization. Despite having enough suns to power quadrillions of civilizations, our entire galaxy represents a minuscule fraction of cosmic existence. Astronomers classify the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars. Smaller, dwarf galaxies number only a few billion stellar furnaces. Probabilistic mathematics involved in counting stars within galaxies unveils mind-boggling possibilities for planetary systems. If even 1% of galactic stars harbor Earth-like worlds, then our galaxy would be home to billions of potentially habitable planets. Some of these worlds could be home to civilizations far more ancient and advanced than human society. Others might contain forms of life so alien that we wouldn't have words to describe them. But what makes these numbers truly unsettling is their cosmic insignificance. Every star we have ever observed, every planet we might discover, every potential alien civilization that could exist within our galactic boundaries makes up less than 1% of the matter in the observable universe. Our galaxy, with all its countless worlds, is but one grain of sand on an endless beach. This shift in perspective challenges anthropocentric thinking about our cosmic importance. The ancient belief that Earth occupied the center of creation seems naive compared to modern discoveries about galactic scales. We exist on one planet orbiting one star, among hundreds of billions of others, in a galaxy considered entirely ordinary among trillions of similar structures. 400 billion stars in our galaxy burn with an energy that eclipses any earthly phenomena. Their combined light creates the luminous band that we observe in the dark night sky. Their gravitational interactions form the spiral arms where new stars continue to be born. Their life cycles seed the cosmos with heavy elements essential for rocky planets and biological evolution. All of this cosmic splendor unfolds within our immediate galactic neighborhood. And the next level of cosmic organization makes our entire star city look like a single house on an endless street. On any autumn night, look towards the constellation of Andromeda. That faint, hazy smudge seems unremarkable among the surrounding stars. Ancient astronomers cataloged it as a nebula, assuming it belonged to our local cosmic neighborhood. Modern telescopes reveal a truth that should simultaneously terrify and inspire. You are looking at another galaxy, containing more than 1 trillion stars. The Andromeda Galaxy stretches for 220,000 light-years across, which is more than twice the diameter of our Milky Way. This galactic giant contains so many stellar furnaces that it dwarfs our local stellar population by 3 or 4 times. If our galaxy is New York City, then Andromeda is the entire east coast of the United States. But confirmed measurements show something even more astonishing. Andromeda is hurtling towards us at a speed of 250,000 miles per hour. This cosmic collision course will culminate in the most spectacular event our solar system has ever witnessed. Computer simulations show that in 4.5 billion years, these two galactic titans will merge in a gravitational dance that will last for several billion years. The collision will transform both spiral structures into a single elliptical galaxy, which astronomers have already nicknamed Milky Way. During this merger, our solar system will most likely remain unscathed. The vast spaces between individual stars mean that stellar collisions are extremely unlikely, even during galactic impacts. Instead, gravitational forces will fling our Sun and its planets into new orbits around the merged galactic center. The Earth could find itself in the outer regions of a merged galaxy, gazing at unfamiliar constellations. And yet, what makes Andromeda truly mind-boggling isn't its size or the impending collision, but what it tells us. Even more unsettling is what Andromeda reveals to us about cosmic scales. Despite being our nearest large galactic neighbor, it is so far away that light takes millions of years to cross that chasm. This distance represents the smallest significant step beyond our local galactic neighborhood. Between our galaxy and Andromeda stretches a void containing almost nothing but dark matter and scattered gas clouds. This intergalactic void has a temperature close to absolute zero and a density lower than in the best vacuum chambers humans can create. Yet, this seemingly empty chasm teems with invisible forces that govern the movement of galaxies through space-time. The approaching merger of our galaxy with Andromeda will create a fireworks display visible from distant galactic neighborhoods. But even this cosmic spectacle is merely a local event in a much larger gravitational theater. Our galaxy does not drift alone through cosmic space. The Milky Way belongs to a gravitational family called the Local Group, which contains over 50 individual galaxies locked in an eternal cosmic dance. This galactic neighborhood stretches for approximately 10 million light-years and holds enough total mass to warp space and time across vast distances. Confirmed observations show that most galaxies in our local group are dwarf systems, containing just a few billion stars each. These cosmic dwarfs orbit around 2 dominant spiral galaxies, our Milky Way and the approaching Andromeda. Much like planets orbiting a binary star system, these smaller galaxies follow intricate orbital paths determined by the gravitational interplay between the 2 largest members of the group. The most well-known dwarf satellites are the Large and Small Magellanic Clouds, visible to the naked eye for observers in the southern hemisphere. These irregular galaxies orbit our Milky Way at distances of 160,000 and 200,000 light-years respectively. Their proximity makes them laboratories for studying galactic interactions in real time. Scientists have discovered that our galaxy actively devours its smaller neighbors. The tidal forces generated by the Milky Way's enormous gravitational pull strip stars and gas from the Magellanic Clouds, feeding our galactic disk with matter. This cosmic feeding process has been ongoing for billions of years, and our galaxy is growing ever larger by absorbing nearby dwarf systems. But this galactic predation reveals something profound about cosmic evolution. Galaxies don't exist as isolated islands floating in empty space. They inhabit gravitational communities where constant interactions shape their structure and evolution. The serene appearance of galaxies in the night sky conceals violent processes unfolding across cosmic timescales. The local group itself moves through space as a single unit. Our entire galactic neighborhood is hurtling towards the Virgo cluster at a speed of approximately 400 miles per second. This motion carries our local cluster of galaxies over distances that dwarf the sizes of individual galaxies. We are passengers on a cosmic vessel sailing through intergalactic space towards gravitational destinations that we can barely perceive. Even more remarkably, the galaxies in our local group are bound together by halos of dark matter that extend far beyond their visible edges. These unseen gravitational frameworks contain 10 times more mass than all the stars and gas we can observe. Dark matter serves as the gravitational glue that holds groups of galaxies together. Despite the expansion of space itself, the orbital dynamics within our local group obey precise mathematical laws governing motion on cosmic scales. Each galaxy traces elliptical paths through space, periodically approaching and receding from its neighbors in cycles lasting billions of years. These gravitational interactions trigger star formation, distort the shapes of galaxies, and redistribute matter across vast distances. Understanding our galactic neighborhood requires thinking on timescales that transcend human experience. The current configuration of the local group is but a single moment in cosmic evolution, spanning tens of billions of years. Galaxies merge, separate, and merge again in patterns too slow for human observation, yet recorded in the motions we measure today. This local gravitational dance is merely the tiniest organizational unit in the cosmic hierarchy, which grows increasingly complex. Galaxy clusters are the most massive gravitationally bound structures in the universe. These cosmic cities contain thousands of individual galaxies, held together by forces so powerful that they warp space and time across millions of light years. The closest large cluster, known as the Virgo cluster, contains more than 1,300 galaxies and is located 54 million light-years from our local group. Confirmed measurements indicate that galaxy clusters should not exist, based on the visible matter we observe. The combined gravitational pull of all the stars and gas within the cluster's galaxies cannot account for the immense forces required to hold these structures together. Galaxies within clusters move at speeds approaching 3 million miles per hour. Such velocities should have scattered the cluster members throughout space billions of years ago. The solution to this enigma required the discovery that most of the cluster's mass remains entirely invisible. Dark matter outweighs visible stars, and gas by a ratio of 10 to 1 in all galaxy clusters. This mysterious substance reveals itself only through gravitational effects on light and matter, creating a cosmic framework that we can map but cannot directly observe. Scientists use gravitational lensing to study the distribution of dark matter within galaxy clusters. Massive clusters warp space so intensely that they act like cosmic magnifying glasses, distorting the view of background galaxies. The degree of distortion reveals how much invisible mass the clusters contain. These measurements confirm that dark matter dominates the structure of clusters, yet remains undetectable by any human-made instrument. The most striking example proving dark matter's existence is the Bullet Cluster, where two galaxy clusters collided at a speed exceeding 10 million miles per hour. During this cosmic collision, the visible gas clouds interacted and slowed down, but the dark matter components passed through one another unaffected. Gravitational lensing maps reveal that dark and visible matter are separated by millions of light years, which is direct proof that this invisible mass exists independently of stars and gas. Galaxy clusters also serve as cosmic laboratories for studying extreme physics. The hot gas between the cluster's galaxies reaches temperatures of 100 million degrees, hot enough to strip electrons from atoms and create a plasma that glows in X-rays. This superheated material contains more mass than all the cluster's galaxies combined, yet remains invisible to optical telescopes. The space between the cluster's galaxies teems with high-energy particles, accelerated to near-light speeds by magnetic fields stretching for millions of light years. These cosmic ray particles generate radio emission, detectable by specialized telescopes, revealing the magnetic structures that bind distant galaxies within clusters. But what truly makes galaxy clusters mind-boggling is their role in cosmic evolution. Clusters represent the ultimate endpoints of gravitational collapse in our universe. Dark matter began to clump together soon after the Big Bang, eventually creating gravitational wells where galaxies formed. Over cosmic time, these galactic clusters merged into progressively more massive clusters. The largest known galaxy cluster, named El Gordo, contains the mass of 3 quadrillion suns and spans 15 million light-years. This cosmic monster is located 7 billion light-years from us, meaning we observe it as it was when our solar system was just forming. Galaxy clusters form nodes in an even larger cosmic structure that resembles a 3-dimensional web. Superclusters are the largest confirmed gravitational structures in our universe. These cosmic formations span such immense distances that it takes hundreds of millions of years for light to traverse them. Our local group belongs to the Laniakea supercluster, a gravitational cluster spanning 500 million light-years and containing over 100,000 galaxies. The discovery of superclusters revolutionized our understanding of cosmic organization. Rather than being randomly scattered across space, galaxies align into vast networks, connected by filaments of dark matter and gas. These cosmic highways guide matter across distances that dwarf the sizes of individual galaxy clusters, creating a hierarchical structure that extends to the largest observable scales. Scientists have mapped our local supercluster by tracking the distinctive motions of thousands of galaxies. While cosmic expansion pushes distant galaxies apart, gravity pulls nearby galaxies towards regions of higher density. By measuring these gravitational flows, astronomers have discovered that our Milky Way and millions of neighboring galaxies are moving towards a massive gravitational center of attraction. This center, named the Great Attractor, contains the combined mass of tens of thousands of galaxies, concentrated in an area hidden by dust clouds in the plane of our galaxy. The gravitational pull of this cosmic monster influences the movement of galaxies over hundreds of millions of light-years, creating currents in the cosmic web that carry entire clusters of galaxies towards regions of increasing density. But the Great Attractor itself is only a small part of an even larger structure. Recent observations show that Laniakea is part of a vast complex of superclusters extending for more than 1 billion light-years. This structure, called the Pisces-Cetus supercluster complex, may represent the largest coherent structure in the observable universe. The implications of supercluster formation challenge our understanding of cosmic evolution. These vast structures took shape through gravitational processes, requiring billions of years to create the patterns we observe today. Dark matter began to clump together when the universe was less than 1% of its current age, eventually creating a framework along which visible matter organized itself. The boundaries of superclusters are challenging to define precisely because they merge with neighboring structures. Unlike galaxy clusters, which are clearly bound by gravity, superclusters are looser associations that can disperse due to cosmic expansion. Some regions within superclusters continue to collapse under their own gravity, while other areas are being stretched apart by dark energy. The shape of superclusters more closely resembles biological structures than geometric objects. Laniakea looks like a massive sheet with tendrils extending in various directions, much like the neural networks within a human brain. This resemblance may not be coincidental, as both systems are organized through processes that create branching, hierarchical structures. Observing the structure of superclusters requires telescopes capable of mapping millions of galaxies across immense distances. The Sloan Digital Sky Survey created 3-dimensional maps, revealing the organization of superclusters by measuring the precise distances to more than 1 million galaxies. These surveys show that superclusters connect, forming even larger structures that resemble a cosmic framework. The cosmic web, emerging from the mapping of superclusters, is similar to soap bubbles floating in space, where galaxies are concentrated along the edges of the bubbles, while vast voids occupy their interior. This soap bubble architecture extends throughout the entire observable universe. Step far enough away from the universe, and you will see an astonishing sight. Galaxies aren't randomly scattered through space, but are organized into a vast three-dimensional network, resembling soap suds floating in the cosmic darkness. This structure, known as the cosmic web, represents the largest scale organization of matter in our universe. Computer simulations confirm that this web-like architecture formed naturally as a result of gravitational processes that began shortly after the Big Bang. Dark matter began to clump together when the universe was only a few 100,000 years old, creating gravitational seeds, which eventually grew into the cosmic framework we observe today. The cosmic web is made up of 4 distinct components, working together across billions of light years. Dense knots mark the intersections where galaxy clusters form. Filaments, or strands, stretch between nodes like cosmic highways, guiding matter over vast distances. Walls form sheet-like structures where filaments intersect. Between these structures lie cosmic voids, containing almost nothing but empty space. Scientists have mapped this cosmic architecture by observing millions of galaxies and measuring their three-dimensional positions in space. The resulting surveys show that galaxies delineate the edges of enormous bubbles, while the voids occupy their interiors. This foam-like structure extends throughout the observable universe with striking consistency. The scale of the cosmic web's components defies human intuition. Individual filaments stretch for hundreds of millions of light years, while maintaining a width of only 20 million light years. These cosmic strands appear incredibly thin when viewed on the scale of the universe. And yet, they contain enough matter to fuel billions of galaxies. Matter flows along the filaments like water through cosmic pipelines, fueling the formation of galaxies in the densest regions. Galaxy clusters form where several filaments intersect, creating gravitational traffic jams that trap matter for billions of years. These cosmic crossroads are the busiest regions in the universe, where galaxy interactions trigger star formation and the growth of supermassive black holes. The most massive clusters mark the spots where the cosmic web reaches its highest density. But what truly makes the cosmic web remarkable is its dynamic nature. This structure continues to evolve as cosmic expansion stretches the universe, and dark energy accelerates the separation between distant regions. The filaments that currently connect distant superclusters will eventually break apart as space expands beyond the reach of gravitational forces. The gas permeating the cosmic web filaments remains largely invisible to optical telescopes, but glows faintly in ultraviolet and X-ray light. This intergalactic medium contains more mass than all the stars in the universe combined. And yet, it is distributed so thinly that a cubic meter of this material contains only a few atoms. Recent observations have detected the warm, hot intergalactic medium, which was predicted to fill the cosmic web filaments. This material reaches temperatures of millions of degrees, while maintaining a density barely above that of a cosmic vacuum. Detecting this elusive component required specialized X-ray telescopes capable of detecting extremely faint emissions from the hot gas. The cosmic web stretches far beyond our current observational capabilities, suggesting that the structures we are able to map represent only a tiny fraction of the universe's organization. Hidden within this web are cosmic voids, so empty they defy our understanding of space itself. Imagine a sphere of space 300 million light years across, containing almost nothing. In this cosmic desert, no galaxies shine. No star illuminates its darkness. No planet orbits in its emptiness. This empty realm, known as a cosmic void, represents one of the most enigmatic regions in our universe. The Botas void, discovered in 1977, is 330 million light-years in diameter and contains fewer than 60 known galaxies. If our local group existed within this cosmic bubble, the nearest large galaxy would be so far away that it would appear as a barely discernible speck in our most powerful telescopes. Confirmed observations show that cosmic voids occupy approximately 80% of the universe's volume. These enormous empty regions separate the filaments of the cosmic web, where galaxies cluster. Despite their immense size, voids contain less than 15% of the average matter density found in other parts of the universe. Scientists initially struggled to explain how such empty regions could exist. Early theories suggested that voids formed as a result of explosive events that cleared matter from vast volumes of space. Modern research indicates that voids are a natural consequence of the cosmic web's formation. As matter condensed along the filaments and walls, it flowed out of the regions that became voids. The emptiness within cosmic voids creates conditions unlike anything else in the observable universe. The temperature inside the voids hovers at only a few degrees above absolute zero. The density falls so low that individual hydrogen atoms can be separated by distances measured in miles, rather than in microscopic scales. These conditions approach an ideal vacuum, which physicists can only create in specialized laboratory chambers. And yet, the voids are not entirely empty. They contain invisible dark matter, which forms a gravitational framework connecting them to surrounding structures. Computer simulations show that void regions contain filaments of dark matter too sparse to gravitationally capture ordinary matter. These invisible threads create a web within a web, spreading cosmic organization into seemingly empty space. Galaxies residing within voids follow different evolutionary paths than their counterparts in denser regions. Galaxies in voids tend to be smaller, bluer, and are more actively forming stars than typical galaxies. Isolation within voids protects these rare galaxies from gravitational interactions that would disrupt their star formation processes. The largest known void, called the giant void or the supervoid in the constellation Canes Venatici, stretches for 1 8/10 billion light-years. This cosmic desert contains so little matter that if our Milky Way were at its center, we would not have discovered the existence of other galaxies until the 1960s. The night sky would appear almost entirely dark, except for our local galactic neighbors. Cosmic voids also influence the cosmic microwave background radiation left over from the Big Bang. Photons traveling through void regions experience slightly different gravitational effects than those moving through denser regions. These subtle temperature variations provide yet another way of mapping the location of voids across cosmic distances. The expansion of space primarily affects void regions, causing them to grow larger over time, while matter continues to drain towards surrounding structures. But even these enormous empty regions appear small, compared to the largest contiguous structures that astronomers have discovered. The largest contiguous structures in the observable universe stretch across such vast distances that they defy the fundamental limits of what cosmic physics should allow. These immense walls and sheets of galaxies span billions of light-years, while maintaining a thickness of only 20 million light-years, creating a cosmic architecture that resembles incredibly thin membranes floating in space. The first galactic wall, discovered by astronomers and named the Coma Wall, stretches for 500 million light-years in length, while being only 16 million light-years thick. This cosmic structure contains thousands of galaxies arranged in a thin sheet, which, when viewed edge-on, would appear as a barely discernible line. The wall is located 300 million light-years from our local group, making it a prominent feature of our cosmic neighborhood. But confirmed observations have revealed much larger structures that push the boundaries of theoretical predictions. The Sloan Great Wall extends for 1.3 billion light-years, making it one of the largest known structures in the universe. This cosmic barrier contains hundreds of thousands of galaxies organized into a coherent pattern that stretches for approximately 1% of the diameter of the observable universe. Even more remarkable is the Hercules Corona Borealis Great Wall, discovered by mapping gamma-ray bursts from distant galaxies. This structure measures 10 billion light-years across, making it so immense that light takes more than 1/10 the age of the universe to travel from one end to the other. The existence of such enormous structures challenges theoretical models of how cosmic organization should evolve. These galactic walls form where filaments of the cosmic web intersect over vast distances. Computer simulations show that dark matter naturally creates sheet-like structures as gravitational forces pull matter together from multiple directions simultaneously. Ordinary matter follows these dark matter frameworks, creating the concentrations of galaxies that we observe. The subtlety of cosmic walls creates gravitational effects that influence the evolution of galaxies across vast distances. Galaxies within the walls experience enhanced tidal forces, which can trigger bursts of star formation or strip matter from smaller neighboring systems. The gravitational environment within the walls differs significantly from the conditions in cosmic voids or dense cluster cores. Scientists use cosmic walls as laboratories for studying the formation of large-scale structure. The precise location of galaxies within the walls provides clues to understanding the initial conditions that existed shortly after the Big Bang. Comparing observed wall structures with computer simulations helps test theories about the properties of dark matter and cosmic evolution. But what makes these walls truly mind-boggling is their role in universal organization. Despite their immense size, cosmic walls are structures of intermediate scale, positioned between superclusters and the largest detectable patterns in the distribution of galaxies. They are components of even larger organizational schemes, which stretch to the very limits of our observational capabilities. The discovery of cosmic walls also reveals the dynamic nature of the large-scale structure. These colossal formations continue to evolve as cosmic expansion stretches the universe. Walls that appear solid today will eventually fragment when dark energy overcomes the gravitational forces holding their components together. Some cosmic walls may stretch beyond our current observational horizon, connecting with structures that we cannot yet detect. This possibility hints at organizational patterns encompassing the entire observable universe. Point the most powerful telescope ever built at any tiny patch of seemingly empty sky. Leave the camera open for several days, collecting every photon arriving from that cosmic direction. The resulting image will reveal something that should fundamentally alter your understanding of existence. This tiny region, no bigger than a grain of sand held at arm's length, contains thousands of galaxies. The Hubble Ultra Deep Field, created by combining 800 separate images with a total exposure of 11 days, revealed more than 10,000 galaxies in a patch of sky covering just 1/13 millionth of the celestial sphere. Each galaxy in this cosmic census contains billions of stars, many of which likely have planetary systems where life may exist. Confirmed analysis of deep field observations allows astronomers to calculate the total population of galaxies in our observable universe. The very latest estimates, based on data from the Hubble and James Webb telescopes, suggest that within the cosmic volume we can currently detect, there are 2 trillion galaxies. 2 trillion is a number that surpasses human comprehension. If you could observe one galaxy per second non-stop, it would take you 63,000 years to see them all. Written out in full, this number requires 13 zeros. 2 million galaxies scattered across the observable space. Each of these galactic islands contains its own stellar populations. Conservative estimates suggest that the average galaxy contains 100 billion stars. Multiplying the number of galaxies by the stellar population yields a cosmic census exceeding 10 to the 24th power individual stars. This number exceeds the number of grains of sand on all the beaches of Earth. But what makes this galactic abundance truly unsettling is how it reallocates significance within the cosmic hierarchy. Our entire local group, containing more than 50 galaxies, represents less than 1/50 billionth of the total galactic population. The Milky Way, with its 400 billion stars, is utterly typical among 2 trillion cosmic neighbors sharing our universe. Recent observations suggest that galaxy counts may actually underestimate universal populations. Improved detection methods continue to uncover faint dwarf galaxies that previous surveys missed. These tiny galactic systems, containing merely millions of stars each, could outnumber large spiral galaxies by tens of times. Observations of the most distant corners of space reveal that the ratio of galaxies is 10 to 1. These deep space images unveil galaxies at various stages of their evolution. Distant galaxies appear to us as they were billions of years ago, when the universe was young, and the rate of star formation far exceeded current paces. These ancient systems possess different structures and compositions compared to modern nearby galaxies, offering us a glimpse into cosmic history. The distribution of galaxies in space resembles a colossal cosmic web, stretching to the very edges of the observable universe. And no matter where astronomers look, the number of galaxies in any direction remains roughly the same. This confirms that on cosmic scales, the structure of the universe appears homogeneous. This homogeneity indicates that the volume we can observe is a representative sample of the universe's entire content. And yet, every new galaxy survey delves ever deeper into space, uncovering new cosmic neighbors that were previously beyond our reach. Every improvement in telescope sensitivity adds billions of galaxies to the cosmic census. The 2 trillion galaxies that we can detect today may only be a small fraction of their total number. Imagine walking along an ocean shore and scooping up a handful of sand. Count the individual grains of sand between your fingers. In a typical handful, you'll find about 10,000 of them. 10,000 tiny fragments of rock and shell, each the result of millions of years of erosion. Now try to mentally count every single beach on Earth. The Caribbean shores, the Mediterranean, the Pacific atolls, and the Arctic coasts. Every single grain of sand on every beach, surrounding every continent and every island on our planet. Scientists have estimated that all the beaches on Earth contain approximately 7 quintillion grains of sand. If you write this number out, it would have 19 zeros, 7 million individual particles. But even this astronomical figure pales in comparison to the number of stars in the universe. Confirmed observations show that there are more stars in the observable universe than grains of sand on all the beaches of Earth. 2 trillion galaxies that we can detect contain enough stellar furnaces to surpass the number of our grains of sand by thousands of times. Every time you pick up a handful of sand, remember this. For every single grain of sand between your fingers, there are thousands of stars in space. And this comparison becomes even more astounding when we consider planets. Modern exoplanet research shows that most stars have at least one planet, and many systems contain entire worlds. If even the most conservative estimates are correct, then in the observable universe, there are more planets than grains of sand on all Earth's beaches, multiplied by the total number of atoms on our planet. Each of these countless worlds is a unique experiment in planetary evolution. Rocky planets orbit in zones where liquid water can exist. Gas giants dominate the outer regions. Icy worlds conceal subsurface oceans. Desert planets are scorched under intense stellar radiation. The diversity of planetary environments surpasses anything science fiction has ever imagined. The mathematical probability hidden behind these numbers leads us to mind-boggling conclusions about life in the universe. Even if life emerges on just one planet out of a million suitable worlds, the cosmos must literally teem with biological activity. Some civilizations could have evolved billions of years before Earth was formed. Others might possess technologies that make humanity's achievements seem primitive by comparison. And yet, the vast distances separating star systems create an isolation that prevents most worlds from ever contacting their cosmic neighbors. The light-speed barrier ensures that civilizations separated by thousands of light years will never be able to establish full contact. Each inhabited world develops in cosmic solitude, unaware of the countless other experiments of consciousness unfolding across the universe. This isolation explains why our night sky seems so quiet, despite the immense number of potential neighbors. Radio signals from alien civilizations would take centuries or millennia to traverse the space between stars. By the time messages arrive, the civilizations that sent them might have changed beyond recognition or vanished entirely. This stellar census also reveals something profound about our place in the cosmos. Every human being who has ever lived exists on one planet, orbiting a single star, among so many stellar lights that there are more of them than grains of sand on Earth. And yet, this incredible stellar abundance is just the beginning of cosmic scales that dwarf even these staggering numbers. The universe you see tonight has boundaries, but these are not physical walls marking the end of space, but fundamental limits imposed by the speed of light and the age of time itself. These boundaries define what astronomers call the observable universe. It is a sphere of space containing everything we can potentially detect with any technology humanity could ever create. Confirmed measurements show that this observable sphere has a diameter of 93 billion light-years. This distance marks the absolute farthest point from which light has been able to reach Earth since the universe began. Beyond this cosmic horizon lies a realm forever hidden from human sight. The calculation of this cosmic boundary demands an understanding of both the light's travel time and the expansion of the cosmos itself. Light from the most distant observable objects began its journey 13.8 billion years ago, when the universe was only 380,000 years old. However, over the course of that journey, the very fabric of space between the source and us has stretched. The objects that emitted that light 13.8 billion years ago are now located a staggering 46.5 billion light-years away. Because of this cosmic expansion, light that departed from distant galaxies when they were relatively close arrives on Earth only after those very same galaxies have been swept away to much greater distances by the expanding space. This creates one of the most paradoxical facts in astronomy. The most distant galaxies we see appear to us as they were when the universe was young and small. However, those very same galaxies are right now far beyond our observational horizon and have already evolved into forms that we will never be able to see directly. The edge of the observable universe coincides with the relic radiation, or the cosmic microwave background. This afterglow comes from the time when atoms first formed and space became transparent to light. This radiation is a kind of baby picture of the universe, taken when it was less than 1% of its current age. But what truly makes the observational horizon mind-boggling is its personal nature. Every observer in the universe has their own unique observable sphere, centered at their location. Alien astronomers in distant galaxies observe cosmic volumes that, in some regions, overlap with our own, while in others, they stretch into spaces we will never perceive. The observable universe continues to grow with each passing day, as light from ever more distant regions reaches Earth for the first time. Each second, our cosmic visibility increases by 1 light second in all directions. Over time, this gradual expansion of our observational range reveals new galaxies emerging from beyond the cosmic horizon. However, this ever-growing field of view cannot expand indefinitely. The expansion of the cosmos will eventually outpace the speed of light, causing distant galaxies to permanently cross the boundary of our observational reach. The observable universe will then begin to contract as the expansion carries our cosmic neighbors beyond the horizon, and we will never see them again. Current observations suggest that we are living in the golden age of cosmic visibility. The observable universe currently contains more galaxies than ever before in history, but fewer than will be visible in the distant future, as expansion isolates us from increasingly distant neighbors. This cosmic frontier raises profound questions about the nature of space beyond our sight. The universe we cannot see may be much larger than the cosmic volume accessible to our observation. The very fabric of space can expand faster than light. This statement would seem to violate Einstein's established cosmic speed limit. However, confirmed observations prove that the fabric of spacetime is expanding at a speed that eclipses the speed of photons racing through the cosmic void. Einstein's theory of relativity prohibits matter and energy from traveling faster than light within space. But such a limitation does not apply to space itself. The universe can stretch its own fabric at any speed without breaking the laws of physics. During cosmic inflation, space expanded so rapidly that regions separated by subatomic distances grew to cosmic scales in less than 1 second. This distinction between movement through space and the expansion of space itself leads to astonishing consequences for our observations. Galaxies at the edge of our observable universe are currently receding from us at speeds approaching 3 times the speed of light. However, these galaxies aren't actually moving through space at relativistic speeds. Instead, the expanding space carries distant galaxies farther and farther away, much like passengers on a cosmic escalator. The galaxies themselves maintain relatively modest speeds within their local space. But the cumulative effect of this expansion over billions of light years creates apparent recession velocities that exceed the speed of light. Hubble's law describes this cosmic expansion through a simple relationship between distance and recession velocity. Galaxies located twice as far away recede twice as fast. 3 times the distance means 3 times the velocity. This linear relationship holds until recession velocities exceed the speed of light at distances greater than 14 billion light-years. The discovery of the universe's accelerating expansion was awarded the Nobel Prize in Physics in 2011. Observations of distant supernovae showed that the expansion rate increases over time, instead of slowing down, as astronomers had expected. Dark energy, which makes up 68% of the universe's contents, drives this accelerating expansion, counteracting the forces of gravity. The current expansion rate suggests that space doubles in size every 10 billion years. This might seem slow by human standards, but cosmic expansion operates over such vast distances that its effects accumulate to colossal speeds on larger scales. The accelerating cosmic expansion means that most of the galaxies we can observe today will eventually disappear beyond our cosmic horizon. Approximately 2 trillion years from now, only the galaxies of our local group will remain visible to future astronomers. The night sky will appear almost empty, with the exception of our galactic neighbors. But the rate of expansion could continue to increase until dark energy overwhelms all other forces in the universe. Theoretical models suggest that the accelerating expansion could eventually tear apart galaxies, star systems, and even atomic nuclei in an event known as the Big Rip. This cosmic catastrophe could occur approximately 22 billion years from now. Nevertheless, the current expansion creates both isolation and opportunities. Space telescopes can observe galaxies at distances where their recession speeds approach the speed of light. These observations provide insights into cosmic conditions when the universe was young, and star formation rates exceeded current ones. The expanding universe also allows astronomers to peer ever deeper into the past by observing increasingly distant objects. Every improvement in telescope sensitivity uncovers earlier cosmic epochs, but the expansion carries much of the universe beyond our permanent observational reach. The space we cannot see may stretch infinitely in all directions. At the very edge of the observable cosmos, a wall of ancient light shines, marking the boundary between the visible cosmos and the unknowable void. This relic radiation, or the cosmic microwave background, represents the most ancient light in the universe. It was emitted when, 13.8 billion years ago, atoms first formed and space became transparent. Before this moment, called recombination, the universe contained too much free energy for stable atoms to exist. Protons and electrons remained separate in a cosmic soup so dense that light could travel only microscopic distances before scattering off charged particles. The universe was literally opaque. Imagine you are inside a glowing fog, so dense that you can't see beyond your outstretched arm. When cosmic expansion cooled the temperature below 3,000 degrees, protons and electrons first combined into hydrogen atoms. This eliminated the charged particles that scattered light, allowing photons to travel freely through space. The universe instantly became transparent, releasing radiation that continues its journey toward us even today. Confirmed observations reveal this background radiation arriving from all directions of space with astonishing uniformity. Modern satellites measure temperature fluctuations of only a few millionths of a degree across this relic background. These tiny fluctuations represent quantum uncertainties from the moment the universe was born, amplified by cosmic expansion, and becoming the seeds from which galaxies ultimately grew. The relic background serves humanity as the universe's baby picture. We observe this radiation as it was when the cosmos was only 380,000 years old, compared to its current age of 13.8 billion years. The patterns frozen in this ancient light reveal the conditions under which the first atoms formed, and cosmic structure began to emerge from pristine smoothness. But this wall of radiation also marks the absolute limit of electromagnetic observations. No telescope can peer beyond the cosmic microwave background, because prior to recombination, light in an observable form did not exist. Earlier, cosmic epochs remain hidden behind this wall of ancient radiation, accessible only through indirect detection via gravitational waves or neutrinos. The cosmic microwave background surrounds Earth like the inner surface of an enormous sphere with its center at our location. Each point on this sphere is exactly 46.5 billion light-years away, representing the maximum distance from which light has managed to reach us since the universe became transparent. However, this observational boundary shifts outwards day by day as cosmic expansion carries the source of the background radiation to ever greater distances. The sphere of cosmic microwave background radiation is constantly growing, but the radiation itself becomes weaker and colder as expansion stretches its waves towards longer, less energetic frequencies. In the distant future, cosmic expansion will stretch this background radiation to such an extent that it will become invisible to any conceivable instrument. The relic background will fade into an elusive whisper, removing even this ancient marker that indicates the edge of the observable cosmos. This radiation boundary raises profound questions about the contents of the cosmos beyond our sight. The universe certainly existed even before recombination, but conditions in earlier epochs remain mostly theoretical. What lies beyond the wall of the relic background might surpass our observable universe in ways we cannot even imagine. Beyond this wall lies a universe that we will never be able to see, but which we know must exist. This hidden region extends backward in time to periods when temperatures exceeded fusion temperatures, and forward in space to distances that may continue infinitely in all directions. Theoretical physics gives us insight into the conditions in the cosmos before the universe became transparent. During the first 380,000 years, temperatures exceeded those found inside stars. Matter existed as plasma, so hot that atomic nuclei could not hold onto electrons. The entire universe glowed brighter than the surface of any star. Even earlier epochs push physics to its theoretical limits. During the first 3 minutes after the Big Bang, cosmic temperatures allowed thermonuclear fusion to occur throughout space. Protons and neutrons combined to form light elements, creating the cosmic abundance of hydrogen and helium that we observe today. This primordial nucleosynthesis occurred when the universe was smaller than our solar system, but already contained all the matter that we can now observe. The first second of cosmic time remains largely a mystery. Theoretical models suggest that during this period, the fundamental forces separated as the expansion cooled the universe below the energy scales, where particle physics no longer applies. First, gravity separated, then the strong nuclear force, followed by the electromagnetic and weak nuclear forces. However, confirmed observations suggest that our universe extends far beyond the cosmic microwave background, not only in time, but also in space. The flatness and homogeneity of space indicate that cosmic inflation expanded the universe to immense magnitudes during the first tiny fraction of a second of its existence. This expansion stretched quantum fluctuations to cosmic scales, creating a space much larger than our observable volume. If inflation theories are correct, our observable universe represents an infinitesimally small part of the total cosmic volume. The region that became our observable sphere was smaller than a proton before inflation began. The expansion increased its size by 10 to the 26th power, and yet, this inflated volume is merely a tiny bubble within a much larger cosmic structure. Modern models suggest that different regions of this greater universe could have evolved under different physical conditions. Regions beyond our cosmic horizon might have experienced different rates of inflation, creating domains where physical constants take on different values. Electrons might have a different mass. Light might travel at a different speed. Gravity might act with a different force. These variations could create cosmic regions where stars form differently, where chemistry follows alternative rules, where life evolves through unimaginable processes. Each such domain could represent a unique experiment in physics, isolated from neighboring regions by an expansion too rapid for communication. Some theoretical models suggest that cosmic inflation continues in regions beyond our observable volume. New space is constantly being formed through eternal inflation, creating an infinite number of bubbles the size of an observable universe within an ever-growing cosmic structure. This possibility suggests that our observable universe, containing 2 trillion galaxies and more stars than there are grains of sand on Earth, represents just one small room in an infinite cosmic mansion. The true scale of existence may stretch far beyond human comprehension or observational capabilities. Scientists, utilizing advanced statistical analysis, have calculated that our observable universe may constitute less than 1% of the total cosmic volume. Mathematical models suggest that the true universe extends at least 250 times farther than the cosmic horizon we can detect, making the hidden cosmos vastly larger than anything humanity will ever be able to observe. This calculation is based on the measurement of space's curvature on the largest observable scales. If the universe were smaller than our observable volume, space would exhibit a noticeable curvature, much like the surface of a sphere. But precise measurements of the cosmic microwave background show that space appears perfectly flat across billions of light years. Flat geometry indicates that the universe extends far beyond our line of sight. The region we see is merely a tiny patch within a cosmic structure so vast that its curvature remains imperceptible across distances spanning our entire observable sphere. It's like standing on Earth's surface. The ground appears flat because our planet is much larger than our local horizon. Even the most modest estimates, based on the flatness of space, suggest that the universe's diameter is at least 7 trillion light-years. This minimum size exceeds our observable universe by 75 times. This means that for every galaxy we can detect, there are at least 5,000 similar galaxies beyond our cosmic horizon. But theoretical models suggest even greater possibilities. The theory of eternal inflation suggests that new space is constantly forming through quantum processes, creating an infinite number of regions the size of an observable universe within an ever-expanding cosmic structure. Each region will contain its own unique set of galaxies, stars, and planets, isolated from neighboring domains by an expansion too rapid for light to ever traverse. This hidden cosmos raises profound questions about cosmic uniqueness. If the universe stretches far beyond what we can observe, then conditions similar to those found in our cosmic neighborhood must repeat themselves countless times throughout this immense structure. Planets identical to Earth could exist in distant cosmic domains. Civilizations equivalent to human society might flourish around similar stellar systems. The mathematical probability in an infinite universe suggests that every possible arrangement of matter must occur somewhere within the hidden cosmic volume. This includes not only Earth-like worlds, but also perfect duplicates of our entire observable universe, repeating themselves throughout infinite space. However, this vast hidden region remains forever inaccessible to human observation or exploration. Even traveling at the speed of light, researchers would never be able to reach regions beyond our cosmic horizon, because the expansion carries them away faster than any signal can propagate. The hidden universe is a realm we can theorize about, but one we can never directly study. Something invisible is tearing the universe apart. Dark energy, which constitutes 68% of the cosmos's content, accelerates the expansion of space with a force so powerful that it overwhelms gravity at distances exceeding the size of galaxy clusters. This mysterious component of reality pushes distant galaxies away from us at an ever-increasing speed. The discovery of cosmic acceleration shocked astronomers who had expected gravitational forces to gradually slow the universe's expansion. Two independent research teams studying distant supernovae in 1998 discovered that cosmic expansion is accelerating, not slowing down. This observation earned them the Nobel Prize in Physics in 2011 and revolutionized our understanding of cosmic evolution. Dark energy behaves unlike any known form of matter or radiation. While ordinary matter becomes less dense as space expands, dark energy maintains a constant density throughout cosmic growth. This means that dark energy's influence grows stronger over time, because as space increases in volume, dark energy's density remains constant. The current expansion rate indicates that space doubles in size every 10 billion years. It might seem gradual, but the constant density of dark energy means that its gravitational repulsion doubles every time space doubles. Thus, cosmic acceleration increases exponentially, creating a runaway expansion that will eventually overcome all other forces in the universe. Confirmed observations show that dark energy currently dominates cosmic dynamics on scales exceeding several 100 million light-years. Within this distance, the gravitational pull between clusters of matter can overcome dark energy's repulsion. Beyond this scale, dark energy wins every gravitational battle, pushing cosmic structures apart, despite their mutual attraction. This cosmic tug-of-war determines the fate of every galaxy we can observe. Galaxies in our local group remain gravitationally bound, despite cosmic expansion. But galaxies in distant clusters are being propelled away by dark energy at speeds that will eventually exceed the speed of light. Most of our cosmic neighbors will disappear beyond our observational horizon within 2 trillion years. The nature of dark energy remains one of the greatest mysteries in physics. Leading theories suggest it is vacuum energy arising from quantum fluctuations in empty space. Alternative models suggest that dark energy changes over time, or that gravity itself behaves differently on cosmic scales. Some theoretical calculations suggest that the acceleration of dark energy will continue to increase until it overcomes the nuclear forces holding atomic nuclei together. This Big Rip scenario will tear apart galaxies, star systems, and, ultimately, even atoms themselves in approximately 22 billion years. Most galaxies visible in today's night sky will disappear from humanity's sight within the next 2 trillion years. The acceleration caused by dark energy will carry these cosmic neighbors beyond our observational horizon, leaving future astronomers with an almost empty night sky, containing only the galaxies of our local group. This cosmic isolation has already begun. Galaxies more than 14 billion light-years away are currently receding faster than the speed of light due to cosmic expansion. Light leaving these distant systems will never be able to reach Earth because space is expanding faster than photons can travel through it. We observe these galaxies only because their light began its journey to us when they were much closer. Computer simulations reveal the chronology of cosmic loneliness. Within 50 billion years, the Virgo cluster will disappear beyond our cosmic horizon. The farthest galaxies that we can observe today will disappear from view, as their light will become too redshifted to be detected. Within 100 billion years, only local group galaxies will remain visible to observers in our cosmic neighborhood. But even this diminished galactic family will face internal changes. The impending collision between our Milky Way and Andromeda will reshape the local group within 5 billion years. Smaller galaxies will be torn apart or swallowed during this merger, which will reduce the number of individual galactic systems in our immediate vicinity. Future astronomers living in the merged galaxy Milkdromeda will inhabit a completely different cosmic environment. Their night sky will contain no external galaxies beyond their local unified system. Deep space will appear empty, except for the cosmic microwave background radiation, which itself will become too faint to detect as cosmic expansion stretches its waves beyond instrument sensitivity. This cosmic isolation creates a disturbing possibility for future science. Astronomers living billions of years from now may have no evidence that other galaxies ever existed. The history of the universe's expansion will be erased from observational records. The Big Bang Theory may never be discovered because the evidence supporting it will vanish beyond detection. We live in a golden age of cosmic visibility that will never return. Earth is at the very center of the observable universe. This statement seemingly places humanity in a special cosmic position, reminiscent of ancient geocentric beliefs. However, this central position isn't a result of cosmic design, but rather the fundamental physics of observation and light travel time. Every observer in the universe is at the center of their own observable sphere. The observable universe is defined as the region from which light has had time to reach a particular location since the beginning of cosmic time. This creates a personal cosmic horizon centered on the position of each observer, making every location the center of its own visible cosmos. Alien astronomers in distant galaxies observe their own unique observable volumes, which in some regions overlap with ours, and in others extend into space we will never see. From their perspective, they occupy the center of the observable universe, while Earth is at the edge of their cosmic horizon. This observational effect is a result of the finite speed of light combined with the finite age of cosmic time. Light from distant objects takes billions of years to reach any observer, creating a natural boundary beyond which nothing can be detected. This boundary forms a sphere around every observer because light travels at a constant speed in all directions. The distance to our cosmic horizon is 46.5 billion light-years in every direction due to cosmic expansion during light's journey. Objects that emitted light soon after the Big Bang were carried to this distance by the expanding space while their ancient photons traveled towards Earth. But our central position comes with profound limitations. We can observe only a tiny fraction of the total cosmic volume, with most of the universe lying forever beyond our detection. Our central position within the observable sphere does not grant us special access to cosmic mysteries or privileged information about the universe's contents. Our central status is merely a coincidence of our specific location. Beyond our cosmic horizon, there could lie an infinite number of parallel universes, each containing different versions of reality, where alternative histories unfold in accordance with quantum possibilities. This multiverse hypothesis naturally stems from the theory of cosmic inflation and quantum mechanics, suggesting that our observable universe is merely one bubble in an infinite cosmic fabric. Models of eternal inflation propose that new space is continuously forming through quantum fluctuations in the cosmic vacuum. These fluctuations create bubble universes, which expand into separate cosmic domains, each potentially developing its own physical laws and containing unique combinations of matter and energy. If eternal inflation proves correct, then every single possible quantum outcome unfolds somewhere within the infinite structure of the multiverse. There exist alternative versions of Earth, where different evolutionary paths have led to variations in history, biology, and the development of humanity. Some parallel Earths may be inhabited by dinosaurs that never went extinct. Others may host civilizations far more advanced than human society. The mathematics of infinite space suggests even more extreme possibilities. Within an infinite multiverse, every single possible arrangement of atoms must occur somewhere, including perfect duplicates of our observable universe, repeating throughout cosmic space. Identical copies of Earth, containing exact duplicates of every single person, would exist in numbers approaching infinity. But these parallel worlds remain forever beyond our reach from our cosmic domain. The expansion rate between various inflationary bubbles exceeds the speed of light by enormous magnitudes, preventing any communication or travel between distinct regions of the universe. Each bubble develops in complete isolation from its parallel neighbors. Some quantum interpretations suggest that parallel universes form every time quantum systems make a probabilistic choice. Every possible outcome branches into a separate timeline, creating an infinite number of parallel realities where every conceivable version of history unfolds simultaneously. The discovery of parallel universes would fundamentally alter human understanding of existence and significance. Every possible version of reality would exist somewhere within the infinite fabric of the multiverse. Our observable universe, containing 2 trillion galaxies and more stars than grains of sand on Earth, might represent an infinitesimally small component of all cosmic reality. Theoretical physics suggests that our entire observable universe, containing 2 trillion galaxies spanning 93 billion light-years, could be smaller than a subatomic particle within a much larger cosmic structure. This staggering possibility arises from models proposing infinite hierarchies of organization, extending far beyond anything humans can observe or imagine. Imagine that every level of organization in our universe operates according to its own laws of physics, its own mathematical principles. What if the physics governing our cosmic scale completely breaks down at higher levels of this hierarchy? This isn't mere fantasy, but a perfectly viable hypothesis. Some theoretical models even suggest that consciousness itself might exist on multiple hierarchical levels simultaneously. Human self-awareness could be merely a low-level phenomenon within vast cosmic intelligences. Intelligences whose thoughts span millions of years and whose information is processed across intergalactic distances. Conversely, neural activity within our brains might contain conscious entities existing on shorter timescales. They experience entire lifetimes in what for us is a mere single thought. And each of these levels of consciousness may not even suspect the existence of the others, even though they share one and the same physical foundation. But the hypothesis of an infinite hierarchy also applies to mathematical reality itself. Perhaps our physical universe exists within a mathematical structure, which is just one part of an infinite library containing all conceivable mathematical systems. This mathematical multiverse would include universes governed by alternative geometries, with a different number of dimensions, or with logical systems utterly alien to us. In such a worldview, physical reality is born from mathematics, rather than mathematics describing reality. Recent advancements in computational sciences have shown how simple mathematical rules can generate infinite complexity through recursive processes. Mandelbrot sets and cellular automata demonstrate how even the simplest algorithms can generate structures with infinite detail at any level of approximation. If reality follows similar principles, then the complexity we observe in our cosmic surroundings might be merely a surface layer of an infinite organizational depth, reaching both inward and outward from the human scale. The discovery of such an infinite hierarchy would render humanity's significance simultaneously infinitely small and infinitely great. We would find ourselves microscopic components within giant cosmic structures, yet potentially containing entire universes within our own physical processes. Each level of existence could harbor forms of organization and consciousness that lie beyond our current understanding. Just imagine that we compress our entire observable universe until it becomes smaller than a single atom within some larger cosmic structure. This thought experiment reveals how insignificant our cosmic neighborhood might be compared to the true scale of existence lying beyond our furthest observational horizon. The size of an atom is approximately 1/10,000,000th of a meter. If our observable universe, spanning 93 billion light-years, were to shrink to the size of an atom, then the larger cosmos containing it would be of unfathomable dimensions. The ratio between our universe and this hypothetical structure would exceed the ratio between an atom and our entire observable cosmic volume. Theoretical models suggest that this scale ratio might be real. The theory of eternal inflation posits an infinite space, containing an unlimited number of regions the size of our observable universe. Each such domain would appear microscopic from the perspective of the infinite cosmic structure containing them all. But the possibilities for scaling go even further. If infinite hierarchies exist, then the very structure containing our universe could itself be smaller than an atom within an even more immense cosmos. This recursive scaling could continue indefinitely, rendering our universe infinitesimally small compared to absolute reality. Advanced theories in physics suggest that the significance of cosmic structures is determined not by their physical size, but by their information content. Our observable universe contains approximately 10 to the power of 120 bits of information encoded in the positions and properties of all particles throughout cosmic space. It is this informational content, rather than spatial extent, that may be the true measure of our cosmic significance. Even if our universe seems microscopic within larger structures, it might contain unique informational patterns that make it valuable or interesting to cosmic intelligences operating on larger scales. The possibility that our universe is merely a subatomic component within larger structures challenges traditional notions of cosmic significance. Every human achievement, every stellar explosion, every galactic collision, all of it could be just microscopic fluctuations within unimaginably vast cosmic processes. Yet at the same time, this ratio of scales could mean that boundless complexity exists even within structures we consider small. If our universe could be compressed to the size of one atom while retaining all its informational content, then individual atoms in our world might contain their own cosmic structures. This fractal organization would mean that complexity exists at every conceivable level, with no fundamental upper or lower limits. As we zoomed in or out, we would discover ever new levels of organization, stretching into infinity in both directions. Recent discoveries in quantum mechanics show that empty space is filled with virtual particles, constantly appearing and disappearing at subatomic scales. These quantum fluctuations might be shadows of cosmic processes occurring within the deep structure of space-time itself. Perhaps all our cosmic surroundings are merely foam upon the surface of a boundless ocean of being. Right now, you are reading these words on one planet, orbiting one star in one galaxy among 2 trillion cosmic neighbors scattered across the observable universe. And all of this vast picture could be smaller than an atom in absolute reality. This perspective places human existence in a context so vast that it calls into question all our notions of significance, purpose, and our place in the cosmos. Earth is 40,000 kilometers in circumference, a tiny rock hurtling through space at 107,000 kilometers per hour around a nuclear furnace that every second burns 4 million tons of matter. Our Sun is a perfectly ordinary star among 400 billion other stellar furnaces populating our galactic neighborhood. The Milky Way galaxy stretches for 100,000 light years and contains enough stellar material to sustain quadrillions of civilizations. And yet, our entire galactic home is but a single grain of sand on an infinite cosmic beach that holds more galaxies than there are grains of sand on all the beaches of Earth. Each of these 2 trillion galaxies is home to billions of stars, and many of them have planetary systems where conditions could support life. By the most conservative estimates, within our observable cosmic volume, there exist hundreds of billions of Earth-like worlds. On some of these planets, civilizations likely arose millions of years before the emergence of human society. But even the observable universe itself might constitute less than 1% of all cosmic reality. Beyond our cosmic horizon lies a universe potentially stretching infinitely in all directions, containing an infinite number of galaxies, stars, planets, and possible civilizations. There might also exist parallel universes where other versions of history unfold, in accordance with alternative quantum possibilities. Infinite cosmic hierarchies could contain our entire observable universe as a microscopic component within unfathomably vast structures. And this view of the cosmos simultaneously renders human existence infinitely minuscule and profoundly meaningful. We are temporary patterns of organized matter that have gained the astonishing ability to contemplate cosmic scales far beyond the scope of our evolutionary origins. Humanity evolved from simple chemical processes on one small planet, yet we have discovered cosmic structures spanning billions of light years. We evolved to hunt and gather food in the African savannas, but we have mapped the large-scale structure of the universe and detected gravitational waves from the collision of black holes. The very same cosmic processes that created galaxies, stars, and planets also created the complex chemistry that led to biological evolution and human consciousness. We are literally made of stardust, forged in nuclear furnaces and scattered across the cosmos by supernova explosions. Every atom in your body, except for hydrogen, was created inside a star that lived and died long before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar nucleosynthesis that occurred billions of years ago in distant corners of the cosmos, far from Earth. This material connection links humanity to cosmic evolution across space and time. We are the universe becoming aware of itself, matter that has attained consciousness and developed the ability to study its own cosmic origins. Even though we occupy a tiny corner of the infinite cosmos, humans have uncovered fundamental truths about reality that are applicable on cosmic scales. We have glimpsed the true scale of existence. The universe is not just more wondrous than we imagine. It is more wondrous than we can imagine. And we are here to bear witness to it.